Hello engineers, welcome back. In this video, we're going to start a new data structure which is called linked lists. I hope you're ready. Let's get started. So in this video, we're going to start with introduction to linked lists. We're going to see what linked lists are. We'll try to understand the structure of a linked list, and then we will perform some operations in code for linked lists, and then we'll discuss time complexities, right? Let's get started. So what are linked lists? So linked lists are another type of linear data structure, just like arrays, which means linear data structure, which means there is a connection between the elements. And arrays had fixed memory, right? This is having dynamic memory, which means we can expand or contract linked list to any size. Okay. And another point is the lifetime of the linked list should be managed manually by the developer or the programmer, right? We need to manage it manually because everything is dynamic. We are putting everything in heap memory. We need to take care of its generation and destruction as well, right? Let's see how it looks like inside the RAM, right? Let's say this is our RAM. On one side we have the stack memory, and on the other side we have the heap memory. So stack memory, we'll be using it for our function calls like main, and then we can have the append method, the remove method, or read method, whatever. So these are the function calls. They are happening here. And the list itself lives in the heap memory. Let's say this is my linked list, and it is carrying a head pointer, and then it lives here. And every element inside the linked list is living inside the heap memory like this. And somehow there is a connection. If this is head pointer is pointing here, one pointer is pointing to the next, other pointer is pointing to the next, and so on. So this is how a typical linked list is seen inside the RAM. Okay, we will discuss the structure in detail, but just to give you a general sense, every node inside the linked list lives in the heap memory and not in the stack memory. And because it is living in the heap memory, it is our responsibility for the creation and destruction of every node. Okay, so let's see how the structure looks like. So we have seen what are linked lists. Now let's discuss the linked list structure. So linked list is a chain of nodes. The nodes are not contiguous like in the case of array. They are lying around randomly in the memory, but they are linked together using pointers. So if this is my node, every node has two things. One is the value and other is the pointer, which is pointing to the next node. And this is the second node, and this is the pointer to the next node. This is the third node. This is pointing to null. So this is the linked list. So these nodes are not contiguous. They are randomly placed. So one node can be here, and second node can be somewhere else like this. Third node can be somewhere else like this, and so on. Okay, there's nothing here. It is null. So that's how a typical linked list look like. And this first node is called the head node. This is where the linked list starts. This is the start point. So if we have access to the head pointer, we have access to the entire list. So from here, we can go through the entire list and do whatever operations we can. Right? So this is how a linked list looks like. Now let's go a step deeper and see how a node looks like. So node is like this, right? There is a value, and there is a pointer. So if this is my class of node, it has one variable for storing the value. It can be int, char, or anything like that. And there is one more self pointer, like pointer of the same class, node star, and this is next. This is holding the value of the next pointer. So if when I'm creating this one, the value will be 1, and next will be the address of the node 2, address of node 2. And if I go inside node 2 will have value equal to 2. Next will be address of node 3. And if I go inside node 3, this will have value equal to 3, and next will be pointing to null, right? So when we reach null, we have reached the end of the list. So that's how a linked list is formed. Okay. So now let's discuss how we can implement all this in code. Let's first try to create a general linked list in C++, and then we will discuss each of these operations in detail. So as we build the structure step by step, it will be more clear to you, as we will use this space to visualize each of our operations, and then we will try to understand how we should do it in code, right? Let's get started. Okay, so I'm in VS Code now. I've created a new folder called linked lists, and this is the first file in it. So I've created the base template. Now we can get started. So we will need two classes. First class is for the node itself. Like I said, node will have two things, int value, and another one is node pointer for next. Okay. So let's make them public so that we can use them in our linked list directly. And whenever we are creating a new node, let's say we are creating this node, initially the next pointer will be null, and the value will be put inside the value variable. So let's create a constructor to achieve this. So node will have a constructor which will take in int value, and we will assign this. So this dot value is value, and next this or this dash next equal to null ptr, null pointer, right? So whenever somebody is creating a node, they will have to give us this value, and we will put it inside value, and next pointer will be null. After that, we can change the pointers to any position so that we'll retain the linked list. So this is how the node looks like. So this is how individual node looks like this. Individually, there is no chaining as of now. Individual node looks like. Now let's see how linked list looks like. So now we'll make the list class linked list. This will have a private variable, and that will be called node star head. Why? Because we need a head pointer, like we said before. If we have access to the head pointer, we will have access to the entire chain, entire linked list. So we just need a head pointer, right? And just as a best practice, we will create a constructor for this as well, just to initialize the head pointer with null. So when we are creating a new linked list, we will have a head pointer which is pointing to null. Okay. Now, how do we create this list? So in the main function, we can simply use linked list. Let's say list 1. We are creating our first linked list equals new linked list. That's it. So Like we have discussed before, whenever we have used new keyword, our list one will be available in heap memory. So if this is the heap memory, here is the linked list. So this is our list one, and it is having a head pointer which is currently null. So our heap memory has the list pointer. Okay. It is not inside the stack memory. So main is started executing here, but we are not putting list one in main because we have used the new keyword. We are putting it in the heap memory. Okay, so our list is living here. So because we are creating the list inside the heap memory, it is our responsibility to remove it at the end. So delete list. We will do this at the end. So we will remember to delete it at the end. Now let's discuss each of these methods. How to add a node to a list, how to append, how to prepend, how to iterate over the list and read every element, how to update an individual node, how to delete from the front, from the back, and things like that. Okay. So let's start with append. So because this is our class, we will put all our functions inside, all our methods for operating on this list. Okay. So let's start with append. Append will not return anything. It will simply append. It will take in a new value. Okay. So let's say I want to append list one dot append. I want to append the node 10. Okay. So I'm taking the value 10. What do I need to do? I will need to create a node first. So I will create a node first, which will look something like this. This is a node. It will have the value 10 with a pointer pointing to null. This is my node. Then first let's create this and then we'll see. So how do we create a node? Node star new node equal to new node of value. So what is happening here? I'm calling on the constructor. Constructor is taking the value 10. Now inside this node, there are two variables, value and next. So value will have the number 10, next will be pointing to null pointer. So my node is created. And as we know, we have used the new keyword. So our node is living inside the heap memory now. Now we just need to chain it like this. Okay. Now, because we are using the method append, we need to check whether this is the first node or there are other nodes inside the list. If it is the first node, which means that this we are inside this linked list and we have a head pointer, right? We will check if this head equal to null ptr, which means there are no nodes. So we can do like this, cout no nodes in the list, creating first node. Okay, so how do we create it? So let's move this node up here. Now we just need to point the head pointer to here. This dash head equals new node. Now we have pointed the head pointer to new node. Now in our heap memory, head is now pointing to this guy, this node. Okay, we have built our first node. Now let's say I want to append another one. I want to append 20. So when we are saying append, it is adding to the end of the list, right? Now we have the first one. Now we need to add to the end of this. So what do? We have come inside the append method and we have created a new node. Now we need to check where to put this node. If it is an empty list, we have directly put it to the head pointer. If it is not, then we will need to travel through the list, find the end node, and then append to it, right? So this is how we can travel. Node star current equal to this dash head, this arrowhead, and then while current dot next is not equal to null ptr, current equal to current dash next, current arrow next. What is happening here? So we have taken a new pointer called current. So there is some new pointer called current. So we are in this append method. Inside the stack memory, we are in this append method. So we have taken a new pointer called current here. Current is pointing to head right now. So where is head pointing? Head is pointing to 10, right? So current will also point to 10. These are pointers, right? So they are dealing with address variables. So current is also pointing here. Now, while current dot next not equal to null ptr, current equal to current dot next. So right now there is only one element inside this list, but imagine there are three elements like this. Let's say we have a linked list like this. So current is here. While current arrow next not equal to null ptr. While current arrow next not equal to null ptr, there is not null here. So we will say current equal to current dot next. So current dot next is pointing to this guy, 20. So we will move our arrow from here to here, and again from here to here. At this point, we will have reached the condition current arrow next will be equal to null ptr. So this is where we will stop, and here we need to append. Here we need to append. So what do we need to append? We will add a new node. Let's say new node is 40, which is pointing to null. Now current is here, right? What do we need to do? The next pointer should point to 40. So we will change this pointer, which was pointing initially to null. Now we will say you can point to 40, and 40 will point to null. Okay? That's how we can append. So let's do that. So we have created a new node. What is a new node? New node is 20, right? So in our heap memory, there is now a new node. Let's say our new node is 20 and null. This is my new node. And what do I need to do? I need to change the next pointer of 10 to point to 20. That's it. Current arrow next equal to new node. And that's it. Okay. So this case is for check if head is null. And this case is for iterate through the list and append. And now after we are done, we can return. So this is the append method. Now let's write a read method so that we can see the output, right? Let's see how our list looks like. So let's create a new method called read. It will not take anything, and it will check first if head is itself null. Then there is nothing to print. We can say cout no nodes in the list, return. If there are nodes, then we need to iterate over each node and print the value. So let's create a current pointer which is pointing to head. Okay, so we are at the beginning of the list. So we will iterate now. While current not equal to null ptr, then we'll do cout current arrow value, and let's put an arrow for better representation, and then we need to take it forward. Current equal to current arrow next, and that's it. After this we can return. So what are we doing? We are creating a current pointer, pointing it to the head, which is the start point of the linked list. We are taking it forward one node at a time and then printing each value. So this is the read method. So let's see how we are doing so far. If there are any code issues, we'll correct them. So list one dot read. So let's call this after every operation. So first I'm appending 10, then I'm reading, then I'm appending 20, again I'm reading. So let's see. Okay, there are a couple of issues. So there are a couple of coding issues, just like semicolons and things like that, which I have fixed. Now our function is working fine. I'm running it again. So as you can see, so when we did append 10, there were no nodes in the list. So creating first node, our list looks like this. And then we appended 20, and now our list looks like this. Okay. So let's add another node. Let's call it 30 and print it again. So let's run it. Okay, now we can see there are 3 nodes in our list. So let's see what's happening here. So when we said append 10, so we created a current pointer, we pointed it to 10, and then we created the node 20, and then we have changed the pointer of 10 from 10 to 20, right? So let's do that. So this is no longer null, this is pointing to 20. And the work of current is done. So all of this will be erased. And this function is coming out of the execution. So append 10 is no longer required. So we have returned to main. And then we did read method, which is just printing out. I'm not adding it here. Then we did append 20, which did the same thing. It created a current pointer, pointed it to 10, traveled to 20, and then added it, right? And then this is returned. And then we did append 30. Append 30 creates a new node. Let's call it 30 null. And what did this do? Again, we've created a current pointer. We started it with head. It pointed to the node 10. It traveled across to 20 and then changed the next pointer of 20 to 30. So this is no longer 20. This will become 30, right? So this is how our list looks like right now. There is a head pointer pointing to 10, 10 is pointing to 20, 20 is pointing to 30. So I'm deliberately putting the nodes in a random order so that you can visualize that lists are not contiguous, right? So we have done append. Now let's do prepend. Prepend is adding it to the first before the list. So we have added 10, then 20, 30. Now let's add before 10. So let's say I want to do prepend list one arrow prepend, let's say 5, and then I will read again. Let's say I want to prepend 5. So let's write our prepend method. So here again, let's check if head is empty. If head is empty, we can directly add it. So let's say list is empty. Adding first node. So we will have to create this node. So how do we create it? Node star new node equals new node of value. Whatever value we are passing here will become the new node. So whenever we are creating this new node, it is in heap memory. But when we are creating this current node, right, it is in stack memory. We have not used new keyword for this. So it is living in stack memory, and it is destroyed automatically after the function execution is done, right? So new node is created. We just need to point it. This dot head equal to new node and return. If it is not empty, like in our case, it is not empty, right? There is 10. So we have created a new node called 5 now, 5 null. So what do we need this node to do? We need to change the head pointer to point to this one, and 5's next pointer should point to 10, right? So let's do the next pointer first. New node dash next equal to this dash head. So whatever is in head is having 10. That will become the next pointer for this. So this is no longer null. This will be pointing to 10. Now we just need to change the head pointer. Head pointer is 10. Now it needs to move to 5. Head is now pointing to 5. So how do we do this? This arrowhead equal to new node and return. Okay. So let's run and see. I'm expecting 5 to be prepended to this list. So our code is working fine. You can see 5 is prepended to the list. Now we have 4 nodes, and just like our diagram, head is pointing to 5, 5 is pointing to 10, 10 is pointing to 20, 20 is pointing to 30, 30 is pointing to null. So this is how our list looks like right now. Okay. And what did we do here? We did prepend 5. All this is done and is done. Everything is returning back to main, right? So just to recap, whatever we are creating inside these methods are living and dying after the function call. But whatever we are creating using the new keyword are remaining in the heap memory. Okay. The list itself is in the heap memory, and individual nodes are also in the heap memory. Okay. So we have already completed prepend and read as well. Now let's see how we can update. So let's say I want to update the node 20 to 25. I want to say update the node 20 to 25. So I'm giving the old value and the new value, and then I will read again. So let's create our update method. It will take old value and new value. So what do we do? First, always we check if head is empty. If it is empty, nothing to update, right? If this arrowhead equal to null ptr, then cout list is empty, return. Otherwise, we will travel through the list to find the old value. So node star current will start at head. We will iterate until we reach the end. Current arrow next is not equal to null. Current equal to current arrow next. So we are iterating. While iterating, if we find the old value, we will just change it to new value. If current old value equal to, current dot value equal to old value, then current arrow value equal to new value, and return. Nothing else to do. Even after iterating the whole list, if we don't find it, we can say cout no node found with given value. Just an additional message. Okay, so update is done. Let's see. Okay, our code is working fine. Now instead of 20, we now have 25. Okay, so that's how we can update any node. If we are updating the first node or the last node, we will traverse through the list, find the node, and then change its value. So that's how we do update. So here in the stack memory, we have done update 20 to 20. And this is done. Now our 20 is no longer 20, 20 became 25. So this is the current state of our list. Okay. So I'm just erasing all this so that we can do more functions. So right now my stack is empty. Only main method is there and my list is currently like this: 5, 10, 25, 30. Now let's do delete. If I want to delete a node, let's say I want to delete the node 10. Let's see how we can do that. I want to delete 10. Delete is a reserved keyword, so I will use the word remove the value 10. And then we will read again. So let's write our delete method. Remove method. It will take one value. Again, we check if head is empty, nothing to delete. If this arrowhead equal to null ptr, cout list is empty, return. If it is not empty, we will go through the list, find the node first. So current will point to head and we will iterate. Okay. When we find the node, what do we need to do? There are two things here. First, if we want to remove the head node itself, then head needs to change to the next node, right? That is one case. Otherwise, we will go through the list, we will find our node and we will change the connections. So let's discuss the case where we need to remove the head first. what do we need if we need to remove the head first? Let's say I've given instead of remove 10, I gave remove 5. Now I come to 5, I will check, oh, this is the head pointer. So what do I need to do? First, whatever is in the next of 5, which is 10, I will change my head pointer to that, and then I will delete this node. Okay. So let's handle that condition. Remove head if this head value equal to value, given value, then this arrowhead will be this arrowhead arrow next, right? So whatever is in the next of head will become the new head, and then now we can remove the current node. So to remove the current node, let's copy it to a new temp node. Temp equal to this arrowhead. This we need to do before changing the next pointers. We will create a new pointer. So if this is my remove 5, I am creating a temp pointer which is pointing to head. Head is pointing to 5. Now I will change the connection of head to this, and now I can remove the temp, right? So I can say delete temp. Okay, that's how we can remove the head node. So let's do that. Let's do that and see. So let's remove the head node first, and let's comment all this for now. And let's say we are deleting the head node. So let's give out a cout removing head node, and return from here. Okay, let's see. See, removing head node. Now our list is 10, 25, and 30. Our 5 is gone. Okay. Now let's remove the node 25. Let's remove something in between. Let's remove 25. So our head removal is working fine. Now I also want to remove 25. So how do I do that? So I need to traverse through the list. When I reach the node, see, let me remove all this. So we did remove 5. So our 5 is gone now. And our head is pointing to 10. Now we are doing remove 5 is done. Now we are doing remove 25. So what do we need? We travel through the list and we reach 25. So our current is now pointing to 25. Now what do we need to do? We need to remove the next of 10 and point it to 30, and we need to remove this chain. So we need to remove this pointer and create a new connection to 30. We also need to remove this connection and make it null. Okay, so to do that we need to keep track of what is the previous node and what is the next node, right? So let's create a previous pointer as well, which will be null pointer to begin with. And as we are iterating, we will make previous equal to current. So let's see how this looks like. So right now I have, let's say my current is here and my previous is pointing to null. As I iterate through the list, I will make current pointing to next one, right? Instead of pointing to 10, my current will now point to 25. And I said, before you do that, you make previous current. Now previous is no longer null, previous is this one. Now this connection is lost. So now previous is holding the previous pointer, previous node, and current is holding the next node. So when I reach 25, now I have access to previous node and current node. I can change the connections now. What do I need to do? I need to remove this connection and make it to null. I need to remove this connection and point it to this one. So what I need to do, previous dash next will become current arrow next. Current arrow next is pointing to 30, right? I need this guy to point to that. So if I do that, the connection is like this now. This is no longer pointing to 25. This will point to 30. So my first step is done. Next, current arrow next, make it null. So we will remove this connection. Now this is pointing to null. Okay, so we have successfully created the connection between 10 to 30 and we have removed this. Now we can delete it. Okay. First, let's find our node. If current arrow value is equal to the given value, then we have found our node to remove. So we can do previous arrow next will become current arrow next, and current arrow next will become null PTR. And now we can delete current and return. Okay. So just to recap, if we found our node to remove, then previous dash next arrow next will become current arrow next. That is our chaining to the next node. And then current arrow next will become null, and then we can remove this. So our linked list will now look like this. This connection is gone. This is gone. This is gone. So 10 is pointing to 30 and 25 is pointing to null, but we have called delete, so everything is removed. So now we just have two nodes, 10 and 30. Let's see. See, removing head node, we removed 5 and then we removed 25 now. Now our list looks like this, 10 and 30. Okay, so that's how we can remove nodes from a list. Okay, now for the final piece, which is the destructor. Now we are left with all this, right? We need to clear all this before coming out of main. Now this is also done. Now we just need to come out of main, but if we come out of main directly, our heap memory will forever hold these nodes until the heap memory is full and we restart the computer. Otherwise, these nodes will always be there. So it is our responsibility to remove them. So let's create our destructor. So how do we create a destructor? Destructor is similar to constructor, just with the tilde symbol in the front. Here let's do cout to check if our destructor is getting called. Okay. So when will the destructor be called? When the scope is done. Delete list one. Okay, our destructor is called. Now inside the destructor method, we will do our operation. So what do we need to do? So first we check if head is empty or not. Cout no nodes to delete. Return. But if there are nodes, we will iterate over each of them and remove them. We need to keep track of connections, so we need to do this carefully. So this is how we used to iterate generally, but let's see if it will work out here. When I'm calling my destructor, so this is all done. When I'm calling my destructor, I'm creating a current pointer which is pointing to 10. Now before I remove 10, I need to hold the next node somewhere, right? So that I can traverse through it. So let's create a temp pointer which is holding the next of current. Now I can delete current, and then current now can become temp. Temp is holding the next value, and current will now become temp, and this loop will continue. Okay, so current is pointing to 10. Now we have a new temp variable. Temp will point to 20, 30, and now we can remove 10. Before removing 10, let's change the connection as well. Now let's say current arrow next, make it null ptr, so we can remove the connection successfully, and then remove. So we've removed the connection to 30. Now we can remove it. Let's remove 10. But as you can see, now head is pointing to something that doesn't exist. So as a good practice, let's make head also as null ptr after going through all this. Okay, so that our entire list is clear. So now head is also pointing to nothing. Now we have 30, which is temp. So current will become temp, right? Current will become temp. So current is not here. Current is here. Temp equal to current dot next. Next has nothing. So temp is also carrying null now. So this is carrying null. Now we said current arrow next is null ptr. So this connection is gone. This is already null. No problem. And then we'll delete current. Current is deleted, and then current equal to temp. Temp is pointing to nothing, so current will point to nothing. And we come out of the loop. Here probably we should do current null ptr, because now current is pointing to nothing. It might throw a heap exception. and that's it. So let's see. After we call our destructor, let's try to read again. Now, when I read again, I want to know, there is the read. I want to see this message, no nodes in the list. Okay, let's see. Okay, so destructor is called, and then our read is called no nodes in the list. So we have successfully executed our destructor as well. So destructor is called, destructor is done, main is done. We have come out of the execution. And because we have called the list one delete, even the list is removed. This entire list is also removed. So our heap memory is back to original state. So we have removed everything. Okay. So I know that was a lot, but my recommendation to you would be to, keep a pen and paper when you're doing linked list questions, because it is all about changing connections. There is not much complexity if you have a pen and paper. It is very difficult to visualize everything when you don't have something to draw on. Okay, so try to keep a pen and paper and visualize everything, because we are changing connections, right? Now let's discuss the time complexities. As you know, append is adding element at the end of the list. So if there is nothing, it will be O of 1. But if there are 100 elements, we need to traverse through 100 elements, and then we will have to append at the end. So first case, this will be O of n operation. Prepend will be O of 1 because we are only changing the head node. We are creating a new node pointing head to it. That's it. Read will be O of n because we are iterating through each node and printing. Update again will be O of n because we need to iterate over the entire list and then find the node. Worst case, the node will be at the end. So we will do O of n operations here. Delete again is dependent on which node we are trying to delete. If it is the head node, it will be O of 1. If it is anything else, it will be O of n. Okay. And destructor will be O of n, obviously. We have to remove every node. Okay. So these are the time complexities. Okay. So I hope you got a good enough introduction to linked list. Do practice it in C++ or any language that you want to prefer. That is it for this video, guys. If you have any questions, definitely ask me. Do check the code and trace it yourselves. Do try to implement it yourself so that it is more clear in your head. Okay. Don't forget to leave a like to this video if you found this helpful. Do leave a comment if you have any questions or suggestions. Do subscribe to the channel so that you don't miss out on any videos. Do bookmark the playlist. Share it with your friends. Thank you so much for watching. I'll see you in the next one. Cheers.